Hello students. The next instruction in the arithmetic group is DADRP, DADRP. So what it does, this instruction is used for adding the content of the mentioned register pair with the content of the HL pair, and the result gets stored in the HL pair only. Again, I am repeating what happens after the execution of this instruction. Suppose a DAD, if I'm writing that B, any register pair you can mention, whether it can be BC, whether it can be DE, whether it can be HL. So whenever you're mentioning the register pair in the instruction, you have to mention that register of the register pair which is holding the highest, which is holding the most significant byte of that register pair. So in case of BC, so B will hold the most significant byte, so that's why I have mentioned B here. So what this instruction will do, that B, what will happen, it will add the content of register pair, whatever register pair is mentioned. Suppose here B I have mentioned, so it will add the content of register pair BC with the content of HL register pair, and the result will get stored in the HL pair only. So here 16-bit addition is taking place. Now flags affected, only carry flag will get affected. Number of bytes for this instruction, as there is no hexadecimal number mentioned along with this instruction, so number of bytes will be 1. Machine cycle, obviously now machine cycle for this instruction, it will need 3 machine cycles. How 3 machine cycles? First machine cycle for fetching the opcode, that is after fetching the opcode and decoding it, microprocessor will get to know that it has to add the content of the HL pair with the content of the mentioned register pair and store the result in the HL pair. So both the HL pair and the mentioned register pair are inside the microprocessor, so it does not have to perform any extra memory read or memory write or input output read write machine cycles, but still it will need 2 machine cycles for complete execution. So as I've told you, first machine cycle is for fetching the opcode. After fetching the opcode and decoding it, what will happen, it will start the addition process. Since it is a 16-bit addition process, and while I was discussing the 8085 architecture, I told you that in 8085 architecture we have a arithmetic and logic unit where all the addition and subtraction or logical operations take place. So that ALU has 2 inputs, one from the accumulator and other from the temporary register, and it has the output. Now what will happen, this ALU performs only 8-bit addition, subtraction or 8-bit operations. Okay, now but this DADRP is a 16-bit addition process. So what will happen, after fetching the opcode, after first machine cycle, second machine cycle will be used, that is a bus idle machine cycle. Means the buses will be in idle state, means there will be no transport or there will be no transfer of address through address lines or address bus, or there will be no transfer of data through data bus. So bus will remain in idle state in this machine cycle, but this machine cycle is used for what will happen for addition process. So how, as I've told you, what is happening, suppose DAD B. So what will happen, it is adding the content of HL register pair with the content of BC register pair. So for performing the 16-bit addition, first what will happen, the least significant byte will get added and the carry flag will get set or reset accordingly, and then the most significant byte will get added. So first the least significant byte addition will take place. So in the second machine cycle, what will happen, the content of accumulator will get stored in a temporary register like W and Z. I told you that there are W and Z registers inside the 8085 microprocessor. So the content of accumulator will get stored in the W register. Next, what will happen, the content of L register will get stored in the accumulator. The content of C register will get stored in the temporary register, and then the 8-bit addition will take place, and the result will get stored in the L register. Carry flag will be set or reset accordingly. Now in this machine cycle, what happened, the least significant byte addition took place. Now this machine cycle is over. Now we need another machine cycle, that too also a bus idle machine cycle. So in that machine cycle, what will happen, the addition of most significant byte will take place. What will happen, the content of H will get stored in the accumulator, the content of B will get stored in the temporary register, and the most significant byte addition will take place in ALU, and the result will get stored in the H, and the content of W register, which was initially the content of accumulator, will come back to the accumulator. So in the third machine cycle, all this process is happening. So ultimately this instruction is will need 3 machine cycles, that is 1 opcode fetch machine cycle and 2 bus idle machine cycles, and these bus idle machine cycles will need 3 T states, that is 3 clock cycles for the complete execution. Now T states, obviously I have told you that opcode fetch machine cycle will need 4 T states, and the 2 bus idle machine cycles will need 3 T states each. So all total 10 T states. So I have written also 10 T states. Addressing mode here, since the addition is taking place between the HL register pair and the mentioned register pair, means the contents or the operands are the content of the register only. So the addressing mode is register addressing mode. So this was all about that instruction. Now next instruction is decimal adjust accumulator. So this instruction, what it does, it adjusts the content of the accumulator to pack BCD after adding 2 BCD numbers. Suppose suppose A is equal to 79 and H is equal to 8A. These two are hexadecimal numbers. So when you will convert these numbers into the binary form, what it will be, 79 will get converted in the binary form like this: 0 1 1 1 and 1 0 0 1, and 8A will get converted like 1 0 0 0 and 1 0 1 0. So what will happen now, these two numbers are written in the binary form, or you can say they are the BCD numbers, they are binary coded decimal numbers. So when you perform BCD addition of these two numbers, what will happen, the result will come out to be what will happen, 0 0 1 1 and 0 0 0 0. So this is the result. But I have told, you might remember this thing, that whenever we are performing BCD addition, if there is a carry from lower nibble to higher nibble, or if there is a carry that is overflow carry, then what we need to do, we need to add 6 to that respective numbers. So what is happening, obviously there is a overflow carry from this lower nibble to higher nibble, so I'll be adding 6 here, that is 0 1 1 0. So I'll get the exact BCD result after the addition process. And here also we have an overflow carry, so I'll add 6 here, 0 1 1 0. So ultimately what will be my result, it will whatever will be the result, that will get stored in the accumulator. So after every BCD addition, whenever you are adding any two BCD numbers, you need to use this DAA instruction. It will actually modifies the result of that BCD into a perfect BCD number. That is mandatory for any BCD addition. Flags affected, obviously all flags will get affected. Number of bytes, since there is no hexadecimal number mentioned along with this instruction, so number of byte will be 1. Machine cycle, obviously it will need only 1 machine cycle, that too for opcode fetch, because because the content of the, here what is happening, the content of the accumulator is being rechecked, because what is happening after addition, after BCD addition, the result will get stored in the accumulator, and after DAA operation it will work on the accumulator content. what this instruction is doing, it is actually performing operation on the accumulator content. Again I am repeating what is happening whenever you will perform any BCD addition. BCD addition can be between any two registers, like register A and any register. The result will get stored in the register A only, that is in the accumulator only. So after every BCD addition you have to use this DAA instruction to adjust the that BCD number stored in the accumulator. So it is actually performing operation on the accumulator's content. So since it is performing operation on the accumulator's content and accumulator is inside the 8085 microprocessor, so one machine cycle is enough, that is opcode fetch machine cycle is enough for complete execution of this instruction. T states, it will need 4 T states. Obviously opcode fetch machine cycle needs 4 T states. Addressing mode, implicit addressing mode, because it is actually operating on the content of the accumulator. That's why the operating addressing mode is implicit addressing mode. Now here we have completed the arithmetic group instructions. So the next instruction is logic group instructions. In the logic group instruction, we'll start with the AND operation. So here I have mentioned 3 instructions and all the 3 instructions perform the AND operation. So let's take the first instruction of the logic group, that is ANAR. What this instruction does, it logically ANDs the content of the accumulator with the content of the mentioned register. Register can be any register like B, C, D, E, HL of 8085 microprocessor. You can write it like ANAC. So what it will do, it will AND the content of the accumulator with the content of the register C, and the result will get stored in the accumulator. Flags affected, here what is happening, this logical group instructions, the 8085 microprocessor is manufactured in such a way that for AND operation all flags will get affected, but carry flag will be in reset condition and auxiliary carry flag will get set. Again I am repeating, for AND operation in the 8085 microprocessor, carry flag will get reset and auxiliary carry flag will get set, and remaining flags will get affected according to the result. The microprocessor has been manufactured in such a way to operate the flags as I've told you now for the AND operation. Number of bytes, obviously there is no hexadecimal number mentioned along with this instruction, so number of bytes will be 1. Machine cycle, obviously it will need 1 machine cycle, and that too for opcode fetch, that is after fetching the opcode and decoding it, microprocessor will get to know that it has to perform logical AND operation between the accumulator and the mentioned register. So the mentioned register and the accumulator both are inside the microprocessor, so it does not need any extra machine cycles for complete execution of this instruction. So only 1 machine cycle is enough. T states, obviously it will need 4 T states, because opcode fetch machine cycle needs 4 T states. So it will need 4 T states for complete execution of this instruction. Addressing mode, since the operand is the content of the accumulator or the mentioned register, so the addressing mode is register addressing mode. Now next instruction is ANAM. So again it will perform the logical AND operation between the content of the accumulator and the content of the memory location which is pointed out by HL pair. So whatever is the content of HL pair, that is the memory location address only, and that content of that memory location address will be used for this logical AND operation with the content of the accumulator, and the result will get stored in the accumulator. Again flags affected, all flags will get affected, and after execution what will happen, carry flag will be reset and auxiliary carry flag will be set. Number of bytes, obviously no hexadecimal number mentioned along with this instruction, so number of bytes will be 1. Machine cycle, it will need 2 machine cycles. First machine cycle for opcode fetch. After fetching the opcode and decoding it, microprocessor will get to know that it has to perform logical AND operation between the accumulator and the content of the memory location. So at this stage microprocessor is having the content of the accumulator and it is having the memory location address which is the content of HL pair. So the next machine cycle will be used for reading the content of the memory location pointed out by HL pair. So next machine cycle is for memory read. So all total 2 machine cycles are enough for executing the instruction. T states, as opcode fetch machine cycle will need 4 T states and memory read will need 3 T states. So all total 7 T states. Addressing mode, since here the operand's address is indirectly specified by the HL register pair, so the addressing mode is registered indirect addressing mode. The next instruction of this logic group is ANI data, 8-bit data. So what it will do, it will perform logical AND operation between the content of the accumulator and the 8-bit data mentioned in the instruction, and the result will get stored in the accumulator. Flags affected, all flags will get affected, carry flag will get reset, and auxiliary carry flag will get set. Number of bytes, obviously 2 byte instruction, 1 byte for fetching the opcode, and the second number of bytes is 2 byte, and machine cycles, we need 2 machine cycles, first machine cycle for fetching the opcode, and the second machine cycle for reading this 8-bit data from the memory, that is memory read. T states, obviously opcode fetch machine cycle will need 4 T states, memory read will need 3 T states, so all total 7 T states. Addressing mode, since here the operand is directly mentioned in the instruction, so the addressing mode is immediate addressing mode. We'll continue with the logic group instructions in my next class. I'm ending this class here. Thank you.